I think I'm finished with chapter 8. How are you all doing on chapter 8? Think you're finished with it? Do you have homework questions or any questions on chapter 8 at all?
Not yet.
Not yet, waiting, saving it? Saving it, okay, today's Tuesday, our test is Tuesday. So we'll spend Thursday reviewing, so that's your assignment. Get yourself organized, get chapter 8 finished, and let me know what it is that you need to spend more time on. Let me see if they can hear me yet. She's still connecting. Anybody hear anything out there? It says my microphone's on. Okay. Okay, I don't trust that you guys can hear me. You probably choose not to hear me. Here. Okay, so I'm going to kind of give you a heads up about something that you should be asking questions on. Here's something from chapter 8, just to kind of quiz yourself. Let f of x equal, I don't know, let's say 4x squared cosine of 3x. Find the ninth derivative of f evaluated at x is equal to 0. With the hint that this function converges or has a convergent power series. On the whole number line. So certainly that x is equal to 0. Nobody's answered me at whether or not you can hear me at home. Can anybody answer me and see if you can let me know if you can hear me? I take that as a no. What if I just said mean things about the people online? Oh, I can't say mean things about people online. Thank you. Okay, so let's think about what it'd be like to take 9 derivatives of this. Your first derivative involves the product rule, right? If you just had find the 9th derivative of this, I wanted that x is equal to 0. I don't want a whole bunch of them. I wanted that x is 0. So your first derivative has the product rule. Your second derivative will have the product rule. Your third derivative will have the product rule. And it gets bigger and bigger and bigger as you take more derivatives. So the plan is, instead of doing that, find that power series that converges to that function. It's a polynomial. Polynomials are easy to take the derivative of. And then if we know that we're evaluating at x is equal to 0, then we don't need to worry about taking the derivative of the terms who will have an x remaining in its expression after you've taken 9 derivatives, right? So I really only need to write this out as a 9th degree polynomial, and who cares about what happens next? So that's what we're going to do. We're going to start with the known Maclaurin series for the cosine of x. Was the cosine the even function or the odd function? It's the even one. So that's kind of easy to remember. So we'll start with the fact that the cosine of x looks like 1. It's alternating, remember that, minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. And I already don't think I need any more terms than that. If I do, it's easy enough to tack them on. Now I want to change that to the power series for the cosine of 3x. So my next step is to replace each x with 3x. Okay, so that takes care of that part. Now the last thing I want to do is multiply this power series by 4x, which means I can distribute it to each term. And it's by 4x squared. So the cosine, so 4x squared times the cosine of 3x should look like, we'll put a 4x squared here, minus 4x squared in front of the 3x squared over 2 factorial plus 4x squared times 3x to the 4th over 4 factorial minus 4x squared times 3x to the 6th over 6 factorial, and there's more. Now let me simplify it just a little bit. When you multiply like bases, you add exponents. And so I can write this as 4x squared minus, let me just write it as 4 times 3 squared, x to the 4th over 2 factorial plus 4 times 3 to the 4th, x to the 6th over 4 factorial minus 4 times 3 to the 6th, that'd be x to the 8th over 6 factorial. I think I'm going to need one more. I'm going to take 9 derivatives. So let's put another one on here. Let's have a negative 4x squared times 3x to the 8th over 8 factorial. Probably should make that to the 10th derivative. I will. Let's change this to the 10th derivative. 10th derivative. Because I'm going to have an x to the 10th right here. Minus 4 times 3 to the 8th times x to the 10th over 8 factorial. And so on. Oh, yes. Yes. Well, I've got that there. Okay, now let's think about what actually happens when we take 10 derivatives of this. Like the first derivative of this will be 8x. The second derivative of this will be 8. The third derivative of that will be 0. This is going to disappear after 5 derivatives, right? I'll have a constant, take the derivative of that constant, and then that one's going to be 0. This is going to disappear after 7 derivatives. This one's going to disappear after 9 derivatives. So this is the only term among these that will be here after 10 derivatives. The term out here would be an x to the 12th. It will still be there after 10 derivatives, but it'll have a value of x in it. It'll have an x squared in it. And I've asked you to evaluate the derivative at 0. So all the terms beyond this one, after you take the 10 derivatives, will contain x to a power. And when I evaluate them at 0, those will all provide me with 0. So this is the only term that will be a constant after 10 derivatives, other than the constant 0. You see what I'm saying? So let's just take 10 derivatives of this term. So these are all going to become 0. These all become 0 after less than 10 derivatives. These terms will all contain x to a power after 10 derivatives. So f10 at 0 will be 0 here. So this is the only term that I'm interested in. So let's watch a few derivatives. So for that term, the first derivative will be 4 times 3 to the 8th times 10x to the 9th over 8 factorial. The second derivative of that one term will be 4 times 3 to the 8th over 8 factorial, 10 times 9x to the 8th. I'll do one more. The third derivative, we'll still have the 4 times 3 to the 8th over 8 factorial. And then I'll have a 10 times 9 times 8, x to the 7th. With that pattern, what will the 10th derivative of that one term look like? 10 factorial times that first bit, right? So with this pattern, we see that f10 at 0 should have this constant on it, 4 times 3 to the 8th times 8 factorial, or over 8 factorial. Then this is going to give me 10 factorial after I do the 10 derivatives. There's not going to be an x on that term, so when I evaluate it at 0, I'll just get that constant right there. Okay? So don't make the mistake of trying to take 10 derivatives here. You can do it. You're all strong enough in calculus that you can do the 10 derivatives, but it's just an exercise in the product rule over and over. Okay? Okay, so did that make you think of anything in chapter 8 that you wanted to ask about? And let's go back to chapter 9. I think we talked about vectors in 2 dimensions and how to add, subtract, multiply by a scalar, take the magnitude, stuff like that. Did we do all of that?
I did a multiplying.
We didn't do any multiplying by vectors, right?
We did it by scalar.
Right, by scalar. Okay, so let me kind of give you a brief overview there. How does that go? Back to there. In sections 9.1 and 9.2, we did our basic vector operations. Right, if you multiply a vector by a scalar, whether it's a one-dimensional vector, two-dimensional vector, or three-dimensional vector, you multiply each component. If you do vector addition, you add component-wise. Same with subtraction. You just distribute the minus sign. In terms of the picture, if this is vector V and this is vector W, the geometric interpretation of V plus W is that it is the resultant vector when these two forces are acting on an object. It'll move down the diagonal of the parallelogram that has these as their sides. So if I try to mimic this length up here and that length over here, then vector V plus W will be right here. So in physics, V plus W would be called the resultant. When two forces are acting on an object, it describes the path of the object as those forces act on them. Vector V minus W can be found the same way, kind of. Here's vector V. There's vector W. If I want to find V minus W, then remember that minus W is a vector. Let me make this shorter so it fits in my room here. V minus W is this vector, but flipped backwards. So that's minus W. V minus W can be thought of as V plus the opposite of W. So now if I make that parallelogram, then this vector is V minus W, V plus minus W. So if I pick that up and glue it on here, it fits right here. V minus W will always have its initial point at the end of W and its terminal point at the end of V. The magnitude of a vector in 2 or 3 dimensions is the sum of the squares of the components under the square root sign. So if vector V has components A, B, C, the magnitude of vector V is the positive square root of A squared plus B squared plus C squared. In most of our applications, we would need a vector that has length 1 in the same direction as a given vector, and we do that to find a unit vector. In the same direction as the given vector V, we just take the vector V and multiply it by the scalar that is its magnitude. So let's rehearse some of these. That one. Here's an example. Okay, plot the points. Point A has coordinates 1, -2, 3. Point B has coordinates 4, 1, 0. And point C has coordinates -3, 5, 2. So I want you to plot the points in 3 dimensions. Then I want you to, in part A, find the distance between points A and B. Then I want you to write the vectors. AB, AC, and BC. And then I want you to find the magnitude of each of these. Magnitude of AB as the vector, magnitude of BC. Yes, I should have done AC, but I skipped it. Do that right there. So to kind of help you visualize three coordinates, I'm going to draw this cube right up here. I have colors. Did not bring any colors today. Well. Come on. So here's how I want you to visualize R3. I want you to think of this edge of the cube as being the z-axis coming up. Here's the origin. This is the positive y-axis. And now coming out of the board like this is the positive x-axis. That help you see more in 3D? I've got a missing edge on my cube. So now, if I were to plot the point 1, -2, 3, let's make that 1 unit. I come out 1 unit on the x-axis. From there, I have to go over 2 units in the y direction. 1, 2. And now up in the z direction, 3 units. 1, 2, 3. So there's point A. Up, back, and up. So I came out of the board, moved back, and then went up. The ordered pair 4, 1, 0. So that's 1, 2, 3, 4. From here, I go 1 unit in the y direction and 0 units over. So there's point B. And now to get point C, I have to go back into the board 3 units. So back in the negative x direction, 1, 2, 3. 5 units to the right, 1, 2, 3, 4, 5. And 2 units up. And there's point C. So that's back into the board. That's gone back inside. Okay? Okay. Now to measure the distance between points A and B, we're looking at the length of this segment here. How do you find the distance between points in 2 dimensions? What's the distance formula look like? Yeah, you make the Pythagorean theorem, right? The distance is really the hypotenuse. So you take the length of each leg, square them, add them together, and then take the square root. The length of each leg, depending on which direction we are, is difference in x's or difference in y's. 3-dimensional analog is the same. The distance will be the difference in the x's squared, plus the difference in the y's squared, plus the difference in the z's squared. So the distance between any 2 points will be the square root, change in x, squared, change in y, squared, plus change in z, squared. And if ever in one of your classes you find yourself in n dimensions, this applies to n dimensions as well. You just take the difference in each dimension. Square them, add them together, take the square root. The order in which you subtract them doesn't matter because we're going to square them. So for our 2 points A and B, 4 minus 1 is 3. So I'm going to square that. 1 minus a negative 2 is also 3. And 0 minus 3 gives me another 3 squared. So I have 9 plus 9 plus 9, or the square root of 27. And that's easy enough to simplify as 3 times the square root of 3. Now tell me how to find the vector representation. How do I write a vector in 3 dimensions? If I know the coordinate. I want to do that. That. How do I get vector AB from the coordinates?
Put in those little caret things.
Put them in the little brackets and have what goes in there. How do I get the x? How do I get the x component? Subtract, but you take the coordinates of the terminal point minus the coordinates of the initial point. So here we'd have 4 minus 1. And the next one I have 1 minus a negative 2. And the next one I have 0 minus 3. Order is important when you're forming the vector. So it's 3, 3, negative 3. Or if you like the IJK notation, it's 3i plus 3j minus 3k. Well, remember what the I, j, and k are. If you're in 3 dimensions, the I basis vector is the vector whose components are 1, 0, 0. The j basis vector is here. It has as its component 0, 1, 0. And then k is up here. And it looks like 0, 0, 1. Those 3 vectors form a basis for all the vectors in R3, which means every R3 vector can be written as a linear combination of the I, j, and k. Okay, so let's keep going. AC, take the coordinates of C, subtract off the coordinates of A. So I'm going to have negative 3 minus 1 is negative 4. 5 minus a negative 2 is 7. 2 minus 3 is negative 1. For BC, I take C minus B in terms of coordinate order. Negative 3 minus 4 is negative 7. 5 minus 1 is 4. 2 minus 0 is 2. Now the length of each of those vectors. Square each component, add them together, take the square root. On your mark, set, go. The length of AB is 3 squared plus 3 squared plus negative 3 squared. And if you've seen that before, the length of a vector is exactly the same as the distance between 2 points. It's the same formula. That's where they came from. Length of a vector is the distance between 2 points. So for BC, I've got -4 squared plus 7 squared plus -1 squared under the radical sign. So that's 16 plus 49 plus 1. 56 squared is 66. And for, oops, I knew when I wrote them in the wrong order, that would happen. That's the length of this vector. So let's change this to an A. And that one to a B. All right, now for the length of BC, I have -7 squared plus 4 squared plus 2 squared. So 49 plus 16 plus 4. So 20 plus 49 is square root of 69. Where's 69? You okay with my numbers? So the distance formula is the same as the magnitude. You know what else the distance formula gives us in 3 dimensions? Think in 2 dimensions what the distance formula did. In 2 dimensions, we defined a circle as a set of all points x and y, the same distance away from a center HK. So we used the distance formula to write the distance between the ordered pair x, y, and HK, and said that was equal to the number r. So it's used to give us the equation of a circle in 2 dimensions. In 3 dimensions, a sphere is a set of all points equidistant from a given center. So let's take a minute and go to coordinate geometry. Let's back off of vectors for a minute, and let's go to some coordinate geometry. A sphere is the set of all points x, y, z that are exactly r units from its center. Let's call the center ABC. So that means that if I use my distance formula, that x minus a all squared plus y minus b all squared plus z minus c squared under the square root sign is equal to r. Or if I square both sides, that's the equation of a sphere with center A, B, C. So I want you to describe the sphere x squared plus y minus 2 squared plus z plus 1 squared is equal to 16. Describe that sphere. Tell me where it has its center and what is its radius.
So it's centered at 0, or 0, 2, -1, raised 4.
Good, good. Right, I haven't shifted away from the origin, so the center is at 0. This moves it 2 units in the y direction, positive y direction. This moves it 1 unit in the negative z direction. So its center is at 2, 0, 0, 2, -1. This is the radius squared, so the radius is 4. Okay, do the same. Let me move to the other side of the board here, so I gotta erase some stuff and switch the camera. Okay, I claim that this thing that I've written up here, and I hope to show everybody else, x squared plus y squared plus z squared plus 4x minus 6y plus 2z equals 10 is a sphere. And I can tell it is because if I were to multiply out this general form, I would have my three variables squared and added to each other, all with the same coefficient. So it's this part that tells me I have a sphere. Now, if I put a number up here different from the numbers in here, then my sphere becomes more oblong. That would be called an ellipsoid. So it looks like a sphere that's been sat on for a while. But when all the coefficients are the same, you've got a sphere. What I want you to do is put it in that form so that you can tell me what its center and its radius is. So I need you to complete the squares on each variable and tell me the center and its radius. See if you can remind yourself how you complete the squares. It's probably been a while since you've done it. Let's first move the terms around, put the x's with the x's, and then leave a gap. Put the y's with the y's, and the z's with the z's. And then in each case, we're adding a number inside so that that rest of the trinomial factors is a perfect square. So you can add a number here, but to balance the equation, you add it over here as well. You add a number here, add it to the other side as well. And then add a number here, and then add it here. You're looking for the number that makes those expressions, those binomials factor as perfect squares. Remember how to get those numbers? Over 2 squared. Take the middle term, divide it by 2, and square it. So here we take the 4, divide it by 2, square it, put it in there. Half of 4 is 2, 2 squared is 4. So I'm adding a 4 on each side. You don't really need to worry about the sign because we're squaring this. So half of 6 is 3, 3 squared is 9. Half of 2 is 1, 1 squared is 1. Now when you factor them, each factor takes the sign of the middle term. So this will factor as x plus 2 all squared. The next one factors as y minus 3 all squared. And then finally z plus 1 all squared. And 24 on the right-hand side. All right, so call out the center.
-2, 3, -1.
And my radius, the best I can do is say it's the square root of 24. Okay? All right, now I'm going to talk a little bit more about graphing in 3 dimensions. If I were to graph a circle in the xy plane, x squared plus y squared is equal to 4, and now project that into 3 dimensions, then x squared plus y squared is equal to 4 for all values of z. So what that would give me is a cylinder centered along the z-axis, right? So if I draw me that circle, if this is 2 and 2, and I draw this circle, x squared plus y squared is 4, and of course it goes back in here, but it's valid for all values of z, and so that would be called a right circular cylinder. I'd have to put a top on it somewhere, but in theory, there is no top to it, it just extends. So in 2 dimensions, a circle becomes a circular cylinder. So if I wanted to graph y squared plus z squared is equal to 1, now my circle's in the yz plane with intercepts at 1 on the y and z axis. So here's the z, here's the y. All right, so I've got this circle here. And now x is coming out here and going back in there. So I've got this right circular cylinder centered about the x-axis. Now for the next one, I just want you to visualize this. Let's say that, let's see how I want to do this. Let's say the floor is the XY plane. And there's the y-axis, and there's the x-axis. And we're talking about graphing y is equal to the sine of x. So I'm standing on these curves that go up and back between 1 and -1 on the x-axis, right? -1 and 1 in the y direction, and then hitting pi and pi, -pi. Now visualize what that looks like when I add the 3rd dimension. Can you describe that to me? Graph of y is equal to sine of x in R3.
Looks like a ribbon candy.
It does. It looks like a ribbon candy. Or a curtain, maybe, coming up. That'll still be called a cylinder. This will be called a circular cylinder, a right circular cylinder. But in general, cylinder in 3 dimensions is any sheet type object. Doesn't have to be closed. Okay, so it'll be a cylinder with the trace of y is equal to sine of x in the xy plane. The trace describes what it looks like in 2 dimensions. Okay, so let me see if you know what this graph would be in 3 dimensions. First degree equation in 3 variables. What do you think that looks like? Who said it?
Like a wall.
Be like a wall? Be like a wall? That's called a plane. It's a plane in 3 dimensions. First degree equation in 2 dimensions is a line. In 3 dimensions, it's a plane. When we draw planes in 3 dimensions, we typically only draw their traces in each coordinate plane. In the xy plane, it's this line. In the xz plane, it's that line. And in the yz plane, it's that line. So here's how we'll graph it. I'm going to get the intercepts. When y and z are 0, x is going to be 12. When x and z are 0, y is going to be 6. And when x and y are 0, z is going to be 4. My 6 isn't quite far enough out. Let's put it out here. So the trace in the xy plane is this line. The trace in the yz plane is this line. And the trace in the xz plane is this line. But now I want you to use your imagination. A plane has no boundary lines. This plane extends infinitely that way, that way, that way. But that's all you see if you were to just look in the first octave. Okay? So even though we draw them so that they look like little triangular regions, this is a plane going in every direction. Okay? Now, in 3 dimensions, we're going to characterize a plane by its slant that it has, similarly to the way we characterize a line by its slope. But in 3 dimensions, I can't name the slope of a plane based upon the lines that are in the plane, because there are infinitely many lines in the plane, all with different slopes. So the slope of a plane is not going to be the same as the slope of a line in that plane. When we talk about how a plane is characterized, it's going to be characterized by a vector that is orthogonal or normal to the plane, which means it makes a right angle with any vector that lies inside the plane. So vectors will be used to help you come up with these numbers when you write the equation of the plane. Which reminds me, in 3 dimensions, if I want to write the equation of a line, then I have to think of the characteristics of slope in 3 dimensions, and those are going to be given by vectors. We're going to need to know a point on the line, and we're going to need to know what the x direction looks like, what the y direction looks like, and what the z direction looks like, and put them together in some way. It'll be a parametric form to write the equation of a line based upon the x, y, and z vectors, giving the line its direction. Those will be called the direction vectors of a line. You'll do that your first week in Cal 3. You'll write equations of planes, equations of lines in 3 dimensions using vectors as parts of their formula. Okay. So that means we need some more vector operations above addition and subtraction. So now I'm going to go into section 9.3. We're going to have 2 operations that are somewhat related to multiplication. The first one is going to be the dot product between 2 vectors. I'll show you how to calculate it, give you about 3 applications of it. And then next class meeting, we'll talk about the cross product of 2 vectors. Or if I have time, I'll do it today with the hay, and give you some applications of that. In your physics, you probably used the dot product. To do what? But for what reason? I mean, you didn't do it just for funsies, right?
Well,
You were computing something. No? Funsies? Just for funsies. And I thought my class was the only one we did things just for funsies. Okay, so section 9.3, the dot product. good news. I was supposed to go to the baseball game today in Amarillo, and we were supposed to leave in the middle of the afternoon. So I made myself get up 6 o'clock this morning so I could get my workout in. Game's been canceled. I could have slept.
No, at least your workout.
I know, but I did kind of a half-a workout. I didn't kind of. I know I could have slept. But I'm glad I don't have to sit outside in the cold and watch a baseball game. And now I gotta think of what to cook for dinner. All right, let's take vector V with its components A1, B1, C1, and vector W with its components A2, B2, C2, where those are numbers. The dot product between the two vectors will be written with a dot between them. And you read it just like that. You say V dot W. V dot W is a scalar. That means it's not living in the pretty little brackets. It's just a regular old number that we get by multiplying component-wise and then adding together. So it is obtained by multiplying A1 times A2 plus B1 times B2 plus C1 times C2. And since multiplication of real numbers is commutative, the order in which I compute the dot product doesn't matter. V dot W is the same as W dotted with V. Order doesn't matter. So for example, if my vectors are 3, 2, -1, and I dot that with 1, 5, 10, then that gives me the real number 3 times 1 plus 2 times 5 plus -1 times 10. That's 3 plus 10 minus 10 gives me 3. Easy enough? All right, so one thing we know about the dot product is it's a scalar. Another thing that we know is that it's commutative. Let's rename that first vector, vector V. And I want you to compute V dotted with itself. And what'd you get? 14? 3 times 3, 2 times 2, -1 times -1 is 14. So it's the same as doing the first component squared plus the second component squared plus the third component squared. So this is the same thing as the magnitude squared. So there's your next fact about the dot product. The dot product between a vector and itself is the same as the square of the magnitude. So now let me show you a couple of applications of the dot product. If I draw some vectors in standard position, let me just do them in 2 dimensions so that my derivation is not that long. Let's say that this is vector V and this is vector W. And I want to find the angle formed by these 2 position vectors. And let's say that this is at the origin. This is at the point A1, B1, C1. Oh, I said I'm in 2 dimensions. Let's knock off that third dimensions. A1, B1, 0, 0, A2, B2. Oops, I got to move way the heck over. Way the heck over. And make it a bit bigger. All right, how many remember your trig on how to find an angle in an acute triangle? Let me make this triangle here. What's the name of this vector right here that I've just drawn? That's V minus W. In your trig class once upon a time, a long time ago, there was a formula that helped you find the measure of an angle that is interior in an acute triangle.
Yeah.
Yeah, there's something like that.
That's the law of cosines.
The law of cosines. We can find that angle using the law of cosines. The law of cosines says something like this. Say this side squared of a triangle is equal to this side squared plus that side squared minus 2 times length of this side, length of that side, times the cosine of that angle. So in general, our law of cosines looks like this. If this is vertex A and that's side A, vertex B and side B, vertex C with side C. And let's put our angle right here. Then the law of cosines says that B squared is equal to A squared plus C squared minus 2AC times the cosine of that angle nestled by vertex B. So in our picture, the length of this side squared, the length of V minus W squared is equal to the length of V squared plus the length of W squared minus 2 times the length of V times the length of W times the cosine of angle theta. If my vectors are position vectors from the origin, then vector V just has those coordinates as its components. And vector W has those coordinates as its components. And so vector V minus W looks like A1 minus A2, comma, B1 minus B2. And so if I actually found these links in terms of A, B, and the cosine of theta, we would have A1 minus A2 squared plus B1 minus B2 squared. That's the magnitude of V minus W squared. The magnitude of V squared is A1 squared plus B1 squared. The magnitude of W squared is A2 squared plus B2 squared. These will have square root signs on them, so I'm just going to leave that as minus 2, magnitude of V, magnitude of W, cosine of theta. One more step here. I'm going to do the squaring on the left-hand side. And then you'll see a bunch of stuff add out. And you're going to see this show up again. So our dot product is going to come out of this. When I square this, I get A1 squared minus 2A1, A2 plus A2 squared. Here I get the first term squared, so B1 squared. Twice that product, so I get minus 2 B1, B2 plus B2 squared. And then recopy the right-hand side. So when I multiply it out like that, we get like terms on each side of the equal sign. So we can subtract them out and lose them. We're going to lose from both sides the A1 squared, the B1 squared, the A2 squared, the B2 squared. So that one adds out with that one. That one adds out with that one. That one knocks out that one. That one knocks out that one. So I'm left with 2 times A1, A2, 2 times B1, B2 with a minus sign. I can pull out the 2 and cancel it with here. I can pull out the negative 2 and cancel it with there. So now divide by negative 2, and you have A1, A2 plus B1, B2 is equal to 2 times the magnitude of V times the magnitude of W times, oops, cancel the 2, sorry. Magnitude of V times the magnitude of W times the cosine of theta. And there's that dot product between the vectors that form the sides of the included angle. So I'm going to rewrite the left-hand side as V dot W, and I'm going to solve for the cosine of theta. Sometimes you'll see this as the definition of the dot product. But I'm going to use this to find the cosine of the angle between two vectors. So it gives us that the cosine of the angle included between vectors V and W is the dot product divided by the magnitude of V times the magnitude of W. So there's a formula for you to help you find the cosine of the angle between two vectors. Now remember, cosine takes any angle and spits out a number between 1 and -1. If I take a vector and divide it by its length, that's a unit vector. And here's a unit vector. So these terms in the denominator guarantee that my right-hand side value is a number between 1 and -1. It doesn't matter whether I'm in 2 dimensions or 3 dimensions. So let's use these as our 2 vectors and write out what the cosine of the angle is for these 2 vectors. Find cosine of the angle between the vector 3, 2, -1 and the vector 1, 5, 10. So I want to point out that in calculus, this angle that we're talking about will come out in radian measure. This formula gives you the angle in radians. And so if you needed to convert it to degrees, how do you convert an angle from radians to degrees? times 180 over pi, right? So there's a couple problems in your web work where it asks for the angle in radians, and one where it asks for the radian in degrees. So to get the angle in radians, we just plug this in. We've already done the dot product. The numerator over there is going to be 3. And now we're going to divide each by the length. So we have that the cosine of theta is 3 divided by, all right, let's get the length here. We got the length of V a minute ago. That was the square root of 14. And now the length of W, I'm going to have 126. So if you used an inverse cosine, that would give you the angle in radians. Multiply that by 180 over pi, that gives you the angle in degrees. Okay? Okay, now when two vectors intersect at a right angle, well, they don't have to intersect if you're in 3 dimensions. 2 dimensions, in 3 dimensions, vectors can be orthogonal if their projections form a right angle. What's the angle? What's the measure of that angle right there? If their right angle in radians is pi over 2. What's the cosine of pi over 2? 0. We can check quickly if 2 vectors are orthogonal or perpendicular if the number over here is 0. The number over here is 0 if the dot product is 0. So that's another use of the dot product. 2 vectors V and W are orthogonal or perpendicular if V dot W is 0. So if and only if goes both ways. V dot W is 0. The number 0 and not the vector 0 because the dot product is a scalar. And I never mentioned it. How can you tell if 2 vectors are parallel? You can tell if 2 lines are parallel, they have the same slope. 2 vectors are parallel if one vector is a scalar multiple of the other vector. Like, for instance, the vector parallel to 1, 5, 10 would be 2, 10, 20. Right? Any scalar multiple of this gives you a vector that has the same direction and the same inclination. So parallel vectors are scalar multiples of one another. So I'll make that quick note. 2 vectors are parallel if one is a scalar multiple of the other. Now, when I asked you what you used dot products for in your physics class, I was hoping you were going to tell me it was work. If you act a force vector on an object in the xy plane, and it moves that object from point P to point Q, then the work done by that force on that object is the dot product between that force vector and vector PQ. Another application of dot product for these folks. Anyway. If a force F is applied on an object and it moves from point P to point Q, then the work done in doing this, remember work is force times distance, so here it's force dotted with the vector PQ. Back it on P, it moves down here, and that force moves it to point Q, where it is the dot product between the force and the distance. Many applications involve using something called a projection vector. So let me quickly show you what the projection of vector V onto vector W is. Let me just draw vector W as being horizontal. It doesn't have to be. And then vector V up here. If the sun were directly overhead right here, and it created a shadow for vector V on the ground that is vector W, that vector here is the one that I'm referring to as the projection vector. This is the projection of vector V down onto vector W. So it's a vector that has the same direction as vector W. In other words, it's going to be some scalar multiple of vector W. Let's see if I can figure out how to do this. That's a right angle right there. And so, let's see. Let's look at this angle here. From our right triangle trigonometry, this vector would be the adjacent side. This would be the hypotenuse. So the cosine of this angle is equal to my projection vector divided by the length of my vector V. So for now, let's just call the projection vector P and start with the statement that the cosine of that angle theta is the length of vector P divided by the length of vector V. If I can figure out what the length of vector P is, then I take a unit vector in the same direction as W, multiply it by the length of vector P, and then I'll have the projection vector. So I'm going to solve this for the length of P. Okay, so far I have that projection of vector V onto W is equal to, I said I'm going to take my vector W, get a vector that is a unit vector in the same direction as vector W, and multiply it by this length. So what I'm going to do now is simplify this in terms of our cosine, where the length of vector P is given by V multiplied with the cosine of theta. from before, the cosine of the angle between two vectors is the dot product of the two vectors divided by their lengths. So I'm going to write the cosine of theta as v dot w divided by the length of v times the length of w. And now I'm going to substitute that in right here. And so I have the formula for the projection vector. Projection of vector v onto vector w is w divided by its length multiplied with this. Well, the magnitude of these are going to cancel. Those are just numbers. So it's multiplied with the number that is v dot w divided by the magnitude of v times the magnitude of w. So all of this stuff, these are all scalars. So it's that scalar multiple of w. That number in the parentheses is often called the component of vector v onto w for the, let's just call it that because I don't have my book on me. Or the scalar projection. It's the scalar that we multiply this unit vector by to get the projection vector.
So vector Q will obviously not be smaller than vector V.
No, it has to be enough. It can be an extension of the vector.
So like V doesn't have to be the hypotenuse of the triangle.
I can reorient space to make it such. Right? In 3 dimensions, I can just kind of look at it from a different perspective. So that's our third application. And so if we go back to our 2 vectors, if V look like I erased them, so let's just make 2 new ones. V has components 1, 4, and W has components 2, 1, then the projection of vector V onto vector W is quickly calculated. We first make a unit vector out of vector W. And then we divide it by, I said V dot W. Oops, I canceled this one. Sorry, take that out of there. I thought that looked funny. Remember we canceled that one with that one? V dot W divided by the magnitude of W. So here's vector W. Quick, what's the magnitude of vector W? Square root of 5. 2 squared plus 1 squared. V dot W. Take 1 times 2 plus 4 times 1. So V dot W is 6. And then quickly, the magnitude of W we just did, that's another square root of 5. So that makes the projection vector 6/5 times 2, 1 fifths times 2, 1. You want to write that as 12/5, 6/5, and that's the projection vector. Okay? So we had the cosine of the angle between 2 vectors, the work done acting with a force moving an object from point P to Q, And then the projection is our third application. And then we use the cosine of the angle to tell whether two vectors are perpendicular. Okay? All right, next time, hopefully, we can review a bit for your test on Tuesday. I put a review sheet on Blackboard. If you've got any time, go through it. As much as you can, at least go through the outline so that you know what to expect on the test. All of chapter 8, sorry?
You put up reviews?
For every test I do.
On Blackboard?
On Blackboard.
I missed that.
Jeez. And I don't keep it a secret. I always tell you when I put it out. I put this one up last week. Sir, those are pointy. Those are vectors. The projection is a vector.
I know, but the one, it's.
Oh, this is parentheses. This is parentheses, sorry. That one's parentheses. That's multiplying by a number. Thank you.
Trust you in a lovely homework sheet.
Thank you, thank you, thank you.
Got one of those too.
Hoorah. Man, you carry that big notebook around with you all day?
Yeah, around space in my journal. So sorry, we'll see.
Thank you.
I have 2 pages left on my test.
Then I'll talk slower.
It's probably writing like as much as I write in a week in like my old math class. In a single
Well,
day.
because you fell asleep about 15 minutes into your own math classes.
No,
Now you make it for at least 45 minutes. Did you turn one in to me?
I'm not sure. I think I might have.
I see. That's a challenge. I think you might have. If you did, it's on my desk because I have no graded papers in here. So, yeah, next time, sorry.
Oh, wait, no, I have it here.
Oh.